Okay, so yeah, wave mechanics. It's the direct application of what we've been looking at with infinite dimensions. The relevant space, the Hilbert space, is L2, square integrable functions. And, sometimes we would say it's on, in the Cartesian coordinates, it's the real line raised, to the power d. So it could be, uh, just the real line, particle living on a line. It could be, we usually put a little coordinate here to indicate that it's, position space. It's basically the space of square integrable functions, in d dimensions. But we'll mostly look at one-dimensional problems. And so remember that we have these pseudo eigenstates of position, which are not properly normalized, but are normalized with a direct delta function. So they're not members of our Hilbert space, but we can still use them if we're just careful in applying this orthonormality condition with the direct delta function. And so the idea here is that the functions in the space, we can think about them as, in sort of the so-called coordinate space representation. And we can just think about that as a kind of inner product between the pseudo eigenvector and, some state phi in our Hilbert space, our infinite dimensional Hilbert space. And this is the wave function. And you'll basically never go astray if you think about wave functions in this fashion. It's the state that you're interested in the coordinate basis. So it's a function of the coordinate. And so, we can do some kind of thought experiments or, some mathematics to figure out, what position momentum have to correspond to in this case. So, or what this wave function does, or what the momentum operator does in relation to this wave function. So we'll just focus on single dimensions, or particle living on a line, so d equals 1. So I won't write the vectors anymore. I'll just replace r with some coordinate x. So if we have a state phi and we think about the this thing, maybe it corresponds to a particle localized, right, at some x equals x naught. Like it's sitting there at some x naught. You can think about a particle sitting on a line at some coordinate x naught. This is x, and you got a particle sitting here. So if that's the case, then if we take the expectation value of the position operator, and it's very, very important that you don't, sometimes, we go back and forth between the coordinate and the operator, but they're very different things. This is a real number. It's, somewhere on the real line. This is an operator. And let's figure out, what we can learn about it. Well, first of all, the expectation value of this thing should just be x naught, because that's where the particle is localized. And also, if we can calculate the deviation of the operator away from its mean value, remember this is this fluctuation, and that will give us some uncertainty in the position, right, of the particle. And we can also think about, the symmetries associated with a particle sitting somewhere in some location. We can imagine shifting our coordinates, right, so that the particle is translated. to say x naught plus a. And so if we have that translation, we would take phi to a new state, phi prime, which would correspond to a translated particle. You just move it. And maybe we don't even have to call it prime, but maybe like phi a or something, so some new state. And if we do that, of course, that shouldn't change much about the state. It should maintain, its norm, for instance, should still be normalized properly. So there must be some unitary operator, right? UA, such that when it acts on this phi, right, you just get the particle translated a little bit. And we know that translations, right, if we take two translations, you translate by a plus b, that's the same as translating by a first and then b, or vice versa. So this unitary operator has depends on a parameter, right, that satisfies this group property. So what do we know about that? What can we conclude from last class? Anyone?
Can you repeat that one more time, please?
Say again.
Can you repeat that one more time?
What can we conclude about the unitary operator that depends on a parameter that satisfies this group relationship?
That there exists some Hermitian operator such that it can be expressed as an exponential of that operator.
Yeah, that's right. That's one of the quiz questions. There's Stone's theorem, and it says that we can write u of a as e to the I a times some Hermitian operator. And the Hermitian operator is the momentum. That's if you define the momentum is basically defined in that way. And this must be, and h bar is there for the units. This is what the momentum operator does. It generates translations. We'll see this coming up over and over again, that whenever you have a symmetry, say a rotation or a translation, associated with it will be some unitary operator that performs that operation, either a rotation or a translation. And this very powerful general theorem tells you that there's an observable associated with each of those symmetries. And in this case, it's the observable, meaning a Hermitian operator, of course. And in this case, it's the momentum. That's what the momentum is. That's sort of what it does. And of course, we can derive properties of it, because if we take, for instance, the translated state, and now we calculate this expectation value. Well, what is this? This must be, the original state, and now we can start putting in the u's associated with the translation, right? And this must all be equal to, of course, the translated position, which is x naught plus a, which itself is, the expectation value of the original operator plus, a, we could write like this, right, for a normalized state. So if you look in here, you got this guy, and you got this guy, and this guy. So putting that together, you see that you must have u dagger a x ua is equal to x plus a times the identity. And that's actually a version of the canonical commutation relation. And you can even see that that's the case, because you can let a approach 0. Then you can start expanding these exponentials up here. And what you get is you get The dagger just gives you a minus sign there, so it's 1 minus IA over H bar P. This gives you an X. This gives you maybe I'll put I for identity. This gives you an I plus IA over H bar P. And then this is all equal to X plus A I. And, you know, we have to look at the leading order terms. So you look at the first term here, which is X, but then you have plus IA over H bar times the commutator of X and P. Those are the two cross terms, right? There's the, I guess, yeah, X, 1 times X times P minus this stuff, P times X. So yeah, it's this is equal to, oh, let's see, did I mess up a minus sign a little bit? Yeah. So it's the convention. The convention is it's there's a minus sign here, so I messed that up. This is the minus sign needs to be there to get it to translate in the right direction. So this is a little bit. So this is actually, this should be a plus. Yeah, it was messing up somewhere. This should be a minus. There we go. Yeah, so this is from expanding the dagger. You dagger this operator and this becomes a plus up here. And the operator is defined with a minus, so it's I minus. So here is a minus I. And that's all equal to X plus A I. And so now you see the X's cancel. Then the A's cancel. You can divide it through. You can multiply both sides by I, H bar, and you get that, you know, XP is equal to I H bar times the identity. So yeah, that's a very powerful thing. We just used the property of translations to derive the canonical commutation relations. And, you know, applying Stone's theorem. This kind of thing is very powerful. We'll see when we do rotations, you can use rotations to derive, for instance, the commutation relationships between angular momentum operators. So yeah, very, very powerful general arguments. That's why we do all the mathematics first, so that, you know, I don't have to give you this for free. I can actually argue why it has to be the case just by recognizing what a translated state should look like, you know, and what a translation is, you know, in terms of a unitary operation on a state. There must be some exponentiated Hermitian operator, and that is enough, you know, up to factors of H bar and a sign. That's enough to give you all of the information you need for the relationship between, you know, X and P. So pretty cool. And, you know, worthwhile to think about. There's lots of stuff here that is important. First of all, the Stone's theorem, of course, is probably most important. But then also recognizing that this kind of operation, this happens a lot, where you send some small parameter, or where you send the parameter of your operation, whether it's a translation or a rotation, where you expand it around 0. This is sort of like expanding around the identity. It's when you have a unitary operator that depends on some continuous parameter, it's convenient to expand it around A equals 0, because the first term is always, you know, in the cases we look at, is going to be the identity plus, you know, higher order terms, because it typically represents some symmetry operation, like rotating by an angle, right? If you set the angle to 0, then that's like not rotating it at all. So it's always expanding around this identity. So you always, because, you know, you're expanding this exponential essentially. So you always get this kind of thing where it's the identity plus that Hermitian operator you're interested in. Same thing here with, you know, minus sign. that comes up over and over again, and you use this kind of expansion to derive commutation relations. So yeah, so you expand around the identity to derive commutation relations. A very common theme in quantum mechanics. And you see the mathematics of quantum mechanics gives you this automatically connection between symmetries and observables. You might have seen related things if you've ever seen, if any classes ever, told you about Noether's theorem, that this is somewhat related to that, but it's a little bit more transparent than Noether's theorem because, well, it just comes straight out of the mathematics of quantum mechanics. Any questions about that? Just want to briefly pause here because it's a important kind of calculation. And of course, this kind of thing, this thing, since it just performs a simple translation like that, you can argue using the kinds of things you did on your homeworks, that this works for any function of the X operator. It just takes that function and translates it by A. It's just that's directly from the kinds of arguments you did on homework 2 here. All right, so that's good. Anything about this? You good? Or no? Okay. So what else? So let's go back to our space L2R and ask what these operators actually do on our wave functions. So we want some notion of what these operators do on wave functions. So in this case, the position, right, this is Hermitian, so we can act it over here. That should just give us x times the wave function again. That's sort of straightforward. What's less straightforward is what happens to the p operator. And we'll see that a sensible thing for the p operator to do is to have it be minus I h bar times the derivative of phi with respect to x. And so it makes sense to define p as this derivative operator in position space. I shouldn't have put the little r. It's one dimension, so it's just x here, just space of wave functions. So this is what the operator does on wave functions. It's minus I h bar times the derivative. And you might, in this you can check it satisfies the commutation relation. And there's a theorem that actually shows that this definition of what the momentum operator does, it's unique up to unitary transformations, up to this kind of transformation of the p operator. So, and that's a theorem called the unitary equivalence theorem of von Neumann. I won't go into it, but you can look it up. It's kind of interesting. It just proves that this choice of p and x, how they behave on wave functions, that's basically unique up to unitary transformations. So we never have to really worry about some other way which we can implement these x and p operators. we're just going to go with this and see what the consequences are of doing it this way. But if you want to know why, you can look up this unitary equivalence theorem. It's interesting. Maybe it might be an extra credit thing to look into it. I don't know. But if you look into it and want to chat with me about it, I'd be interested in talking about that. Okay, so let's say some more things that we know. We have these pseudo eigen states X, right, that satisfy. Now we're in one dimension, so you know everything's just functions of a single variable. And we also know from what we just did that, you know, according to Stone's theorem, this is the unitary operator that translates states. So this should translate our little ket to x plus a. And although this is not a proper eigenstate of our, you know, it's not a proper vector in our Hilbert space, we can still use this to calculate. For instance, we have a generalized notion of now matrix elements. For instance, of any function of the operator x, we can think about the matrix elements of this operator. And if we think about what this is, you know, this would act on this, and we can treat it as an eigenket, right? So this would become the function of now f of little x, right, of the number, right? This is a function of an operator, now becomes a function of the same function of a variable now, and this comes out, and so you get f of x, you know, delta x prime minus x, and this is the equivalent of a diagonal matrix, right? Except it's in this distributional sense where instead of having elements, you know, in a finite matrix, you have a function multiplied by this delta function, which states that, you know, this thing vanishes unless x prime is equal to x, where then it blows up. And there's also this notion of completeness, right? And although so you have to keep in mind that these aren't real elements of our Hilbert space, so it's not really like a proper matrix element. But if you're careful in just using this notion of orthonormality, then everything works just fine. You can just still do the same linear algebra that we've been doing for finite dimensions, just keeping in mind this new inner product, and also a new version of completeness, which is instead of summing over a basis, right, you integrate from, if it's the real line, minus infinity to infinity dx of this projector. And now you can use this as a completeness relation to stick into various calculations, just like we did for finite dimensions. So these are the kind of tools that you need to do wave mechanics. And of course, the physics of it is that there's a probability associated with all of this, right? We know that when we take the inner product squared, we should get some probability of being in a state. But here, it's going to be a density. So if we look at the inner product, say, of x with some phi, right, squared, this isn't a pure probability like from 0 to 1. This is a probability density. You have to integrate it in order to get a probability. And it's because essentially, if you look at any state phi, right, if we decompose it using completeness, right, we stick in here an integral dx x x phi. This here is our wave function, as I said. So you see the state itself is not really, it's not a proper sum of over a basis, right? If you're using this x as a basis, then you have to integrate. This is an integral, not a sum, right? So in some sense, a good way to think about it is that this wave function is a kind of state density. It's a state, but per unit length because of the integral. So you want to get a proper state in a Hilbert space, you have to integrate your state density, the wave function. And so in a similar way, when you take the state density and you take the magnitude squared, you get a probability density. And from here, you could calculate various things like the probability of, and of course, this is just the wave function squared. So you can calculate the probability of a particle living in an interval. This is particle in some interval, x in some interval from a to b. The probability of that is going to be the integral from a to b of dx phi of x squared. So it gives you a probability density. You have to then integrate up to get a proper probability, which satisfies the rules of probability. It's between 0 and 1, and so on and so forth. Also, if we consider the translation operation, and this is a kind of fun exercise, you can think about this operator, the p operator, using that derivative notation. You can think about Taylor expanding it, and then you get like a power series of this exponential, right, with powers of the p operator, which are derivatives. So it's like higher and higher order derivatives. And that'll give you a Taylor series. So if you do this and you act on a function, a wave function phi of x, what'll end up happening is that you get phi of x minus a. And this is basically equivalent to, defining p acting on phi, that function is, minus I h bar. I'm going to use this notation now, it just means derivative with respect to x, phi of x. You can check that these two things are completely related. I wonder, why is this minus sign here? It has to be there because if we think about a wave function localized at some x naught, and this is x, phi of x. Then if we translate it by a, right, we move it over to a, and now it's sitting out here. Then this function is phi x minus a, right? Because the peak has to be, well, it's if you're shifting a function over in one direction, then its argument shifts in the opposite way. So you can imagine maybe this peak's at 0 or something, right? If the peak is originally at 0 and now you want it to be at a, right? It's phi of x minus a that has a peak at a, because now x has to be equal to a to get the peak. It's just, it's the usual thing when you translate a function in one direction, the argument goes the other way. It's just something to keep in mind. And it all works out with this definition of the momentum operator. And you can check, and maybe I'll assign it as homework. You can check that if I do this kind of thing, I put in this minus I h bar partial x up here, this gives me e to the minus a partial x. You might wonder what this thing even is, but it's just a Taylor series, right? It's sum over n, 1 over n factorial, minus a partial x to the n. And, so you'll get a Taylor series, basically, of the function. Higher powers of the derivatives, just, first derivative, second derivative, third derivative. If it's acting on a function, you'll get, you know, higher and higher derivatives of this guy. And if you can take this, right, you can write it as a Taylor series around minus a equal to 0. What do you get? Well, you get a sum, 0 infinity, 1 over n factorial minus a to the n power, right? Well, I sort of derived it for you already. And then this is the nth derivative of phi, you know, evaluated at x. It's just Taylor series. So they're the same thing. So it's good to keep in mind that now our operators can be derivatives acting on functions, but the same rules we've been using all along apply. If you see a function of an operator like an exponential, you want to expand it into a power series. And then powers of derivatives just give you more and more derivatives. So just gives you that. So you can actually just derive this directly from the definition of the position operator. So I basically did it right here, but you know, some version of this, you know, will be on the homework. Okay, questions about that? No? You good? Okay, so that's kind of position space. Of course, we don't have to stay in position space. This is all sort of, this is related to the operator x, right? That's kind of the theme here of this section. But we don't have to do that. We could also have, if we want, to have wave functions of momentum if we wanted. So there's also the momentum space representation. So let me clear this now. Okay. So there's also momentum space. And that one is just, you know, associated with this pseudo eigenket, which gives us an eigenstate of momentum. And we can think about this thing. And we should have an associated wave function in position space, which, you know, would be xp. And we can think about what this should be. Well, I mean, we can work it out. For instance, we know that we take p and sandwich it in here. This, by definition, is an eigenstate of momentum, so this should give me a little p xp. But we can also take this p, right, and act on the left. And it's Hermitian, so we can just act on the left for free. And if it acts on the x portion of it, we know that this should give us a derivative operation with respect to x. Now this acts on x p. So you get a little differential equation for this chi of p, right? You get that minus I h bar derivative with respect to x of this chi of p is equal to p times chi of p. And this has a solution. Chi of p, you know, up to normalization is equal to, and I choose this normalization. It's the same as choosing a normalization for Fourier transform, as it turns out. It's just this guy. It's a complex exponential. This is just a solution of this differential equation. So this is an important object. It's the wave function associated with a particle with a definite momentum. It's a pseudo wave function, as you can see, because p is in an improper state. When you try to compute the wave function, right, you get something that's not square normalizable. You can't normalize this thing. all makes sense because we know that this kind of thing is not really a proper eigenvalue equation because P is continuous. So this eigenvector doesn't necessarily have to be a part of our Hilbert space. So then when we calculate the wave function, then it might not be square normalizable. It might, it's not going to be an element of our Hilbert space, which is, L2R. It's okay though, because we sort of knew that's what's going to happen just because, the momentum of a free particle is continuous, has a continuous values. But, it still satisfies, even though that's true, it still satisfies basic properties of orthonormality and completeness just in this distributional sense with Dirac delta functions. So in particular, here's orthonormality. Orthonormality. It tells us that we must have, when we integrate from minus infinity to infinity, dx of chi star at two different values, right? Associated with two different eigen directions here. Then this should just give us, we can use this solution here. It's 1 over 2 pi h bar minus infinity to infinity dx e, what is it here? I over h bar, right? We got a p minus p prime, right? The minus here because it's chi star. This is all we're doing is we're just calculating this guy, p, right? It's p prime p, and we're just sticking in a completeness relation in terms of the x's, and that gives us these two. So really, really good to practice this stuff. Just using the bras and cats, put in the completeness relation here. All the same stuff we did before, except instead of sums, we have now integrations, but it's okay, it's still the same thing. This is a wave function. This is the complex conjugate of the wave function. Same stuff as before. Anyway, so I kind of skipped those steps, but you should really start getting used to these things as we go along here. Just practicing sticking in completeness relations and thinking about, all these things in terms of bras and kets, converting between now integrals. Before we were converting between vector and matrix multiplication. Now we're going to be converting between, bras and kets and integrals, basically. And instead of a delta function, of two discrete variables, you just get a Dirac delta function. And this is a kind of Fourier representation of the Dirac delta function, which you might have seen in some math methods type classes. But this must be what it is, just from the infinite dimensional Hilbert space theorem that we proved, right? That if you have a continuous spectrum like this, like for the momentum operator, this is the orthonormality that you must have. So this must be true, even though you can prove it in other ways, or you can prove it more explicitly by actually just doing this integration if you wanted, showing that it gives you that it's a consistent definition of the Dirac delta function. Okay, and there's also completeness, which kind of looks similar. And remember, completeness should be something like the identity should be equal to, this guy. And if we think about these as matrix elements, well, then we better sandwich them between x prime and x, right? And so then we should get something like this, right? Just by making arguments about bras and kets. So we should get something like this, which is a delta function between the x's, because that's the identity matrix in position space representation, the matrix elements of it. This delta function should be equal to the integral over p of a product of these momentum eigenfunctions. And indeed, that's what you get. This is 1 over 2 pi h bar minus infinity to infinity dp e to the I over h bar, p x minus x prime. So there we go, and this is equal to a direct delta function, the x variables. And this is just basically, you know, the Fourier inversion formulas. Lets you go between Fourier transforms and you know, the original functions of x. You know, you can think about the momentum space as being just a Fourier transformed version of the position space wave functions. So you can use these formulas, these ideas, which come directly from notions of Hilbert space, right? It's just completeness again, inner products. That's all it is, and orthonormality. We can now just have a set, right, of different kinds of wave functions. So we looked at the x one already, and again, just to summarize, is x dotted into our state phi. And if we want to, and this we can connect back up to Fourier transform. This is another wave function, which is now the momentum space representation of the same state. And you can, of course, use these formulas. What can you do in here? You can stick in completeness, right? You can do, this must be dx px x phi, right? Stick in a little completeness relation there. So this tells you that this thing, what it must be is 1 over square root of 2 pi h bar. That just comes from this piece, the px. That just comes from this, the conjugate of chi, which we already know what it is. It's just this guy up here, 1 over square root of 2 pi h. So it's e to the minus now for the, since it's complex conjugate. Yeah, so here we go. It's the integral from minus infinity to infinity, dx e to the minus I px over h bar. And this is just the wave function, phi of x. Same thing for here. We could stick in a completeness over the p's. And what we get is a relationship between the wave function and this guy. We get 1 over square root of 2 pi h bar minus infinity to infinity dx e. This time plus I px over h bar. Because now it's x dotted into p, not p dotted into x. So it's the original wave function, the chi p thing. Phi tilde of p. So you see they're Fourier transforms of each other. Any kind of Fourier. So you can actually use these bras and kets, right, to prove all sorts of fun things about Fourier transforms, because it's all we're doing here. We built up this mathematical structure of the Hilbert space in order to basically prove facts about Fourier transforms. At least that's how it comes out in this L2 space. But it's nice because it's really not any different from what we do in finite dimensions. So it's, you just more practice with this bras and kets, and then, you know, it won't really won't lead you astray very much. And you don't have to remember, like I never remember this stuff anyway. Yeah. So, but you can rely on remembering completeness and inner products and bras and kets to derive a lot of this stuff. So yeah, and I mean, I guess it's a little bit hard to remember the sign convention for the Fourier transform, but again, you can see it's this not inverse thing that I talked about. I forget if it was recitation or not. So if you're Fourier transforming, right, you have phi tilde of p. This is Fourier transform of your function. So it's a forward transform. You're transforming to a new function. Then it's not the inverse, so it's minus I up here. But if you're going backwards from your transform function to back to the original function of x, then it's the inverse transform. So you do a plus I. Anyway, that's just my mnemonic to remember the sign and the exponent. But yeah, any questions about that? These bras and kets, this is,
Should both of those integral be over x, or should the top one be from over
oh.
dp?
Yeah, very good, very good. Yes. Yeah, we're sticking in completeness in P, so. Yeah, this is all properties of these X and P. Pseudo eigenkets, as I would say, or as people would say. But they work just like bras and kets. It works fine as long as you just remember that they have a different. Basically, all you ever have to remember is these guys, right? And that completeness looks a little different. That it's the integral. Other than that, plus bras and kets. That sort of gives you everything. The same with x. X is the same. X prime. Yeah, so it's very powerful stuff. That's why the Hilbert space, it's really nice to develop it first because it applies to all this stuff. It's very hard to remember the wave function stuff, I think. But if you just remember completeness and a few basic facts, then you can derive all this stuff. The momentum and position wave functions are Fourier transforms of each other and things like that. Okay, more questions? Okay, if not, we can think about now, think about the actual states phi. And remember, so if you have actual states, then their associated wave functions are going to be, in L2 R. They're going to be square integrable. They're going to be square integrable wave functions, right? And this is a problem because if we have a particle moving along with some momentum p, that it's nice to be able to think about its wave function as this guy, or sorry, the backwards, x dotted into p. It's nice to be able to think about its wave function as this chi p, this thing that's proportional to e to the ipx over h bar. It's nice to think about it that way, but the problem is that this function is not in our Hilbert space. So it's not normalizable. It's an oscillating thing that just oscillates as a function of x along the whole real line. It's not a very good. It's not square integrable. So what you often do is you construct a wave packet. You take something like this and you just confine it to some region, say in X. And so you can have these crazy oscillations, but, and the oscillations are what tell you about the momentum of a particle, but you can still confine it in some localized region in space with an associated, uncertainty delta X. And we even know what, so we even know what those things are, those uncertainties. And so again, the point is that this thing that's oscillating inside an envelope of some, finite shape that goes to zero, out at infinity, this thing is a proper wave function, right? This thing is okay because it's square integrable, perfectly sensible, unlike this thing in red, which is not. But it's okay because usually we'll see that the shape of the envelope doesn't really matter too much as long as you just put some kind of envelope on it. You're okay, and really all the physics lives in the wiggles, which are described by something like this wiggly exponential. So the idea of the wave packet, again, is you want to confine your states in some finite region, and so then that comes with its associated uncertainties, right, in the position. Now I'm writing this in terms of the wave functions and momenta. We got dp, and the momentum uncertainty is, of course, more convenient to write in terms of a Fourier transformed wave function, function of p. So you got these uncertainties, and you can show that these, using the canonical commutation relation and that general theorem that we derived from the finite dimensional chapter, or or the postulates of quantum mechanics, we can directly translate that for these x and p operators to get that delta x delta p is greater or equal to h bar over 2. Just, we already derived this. This is remember delta a delta b is greater or equal to 1/2 expectation value of the commutator between A and B, and magnitude. Right? And if A and B are x and p, then we just go back and remember that the commutator between x and p is IH bar. I derived that today. So you just get the magnitude of IH bar is just h bar, so you just get h bar over 2. So we'll know that for any sensible wave function, that if you compute these uncertainties, in the position momentum, then you'll get this bound between them. And you see, in this language, it's just like a property of Fourier transforms. It's just a property of wave mechanics. It doesn't even, but we derived it, using notions, general notions about Hilbert spaces and operators on Hilbert spaces. So there's actually a kind of interesting, I'll post this on Canvas later today. There's an interesting YouTube video about uncertainty relations as they connect to just wave mechanics, just the properties of Fourier transforms. So I'll put up a video link later today from a guy who makes nice YouTube videos about it. If you're interested in this uncertainty relation as it connects to wave mechanics in particular, not quantum mechanics, just like properties of oscillatory motion, basically, or properties of oscillations or oscillatory phenomena. Anyway, but we already derived this, so I don't have to say much more about it. And of course, you can use this right away to derive all sorts of cute things if you wanted. We had the Bohr atom, for instance. And the Bohr atom, if you remember, the energy of the Bohr atom was, it's an electron whizzing around some proton. The energy for that, there was a kinetic energy associated with the electron, and then there was a Coulomb interaction between the electron and the proton. And so you can start thinking about this. If this has some orbit r, this is out at some circular orbit radius r, then we can think about its uncertainty and its position as sort of being, at least at the same scale as r. And of course, that means that there's an uncertainty in momentum, delta P associated with that, which will be, if it saturates this bound, and, dropping the factor of 2 is H bar over delta X. So it goes like H bar over R. That's the uncertainty in the momentum. And if you substitute back into here, you'll see that the energy, and if P, if we're in some low momentum state, and if it's dominated, the momentum is dominated by this uncertainty, then the energy should scale at least like H bar squared over 2m r squared minus E squared over R. This is a very hand wavy argument, but this, if you plot this thing, this has a minimum. This has a minimum energy at a non-zero R, which is the Bohr radius. Actually, you can minimize this thing, and you'll find that the minimum is at H bar squared over m E squared. Just by taking dE, dr, setting it equal to 0 and solving. So this is a kind of, you can use the momentum and position uncertainty relation to argue why the electron doesn't just fall into and collide with the proton, right? If you have an electron sort of whizzing around here, and why doesn't it just fall into here? It wants to. I mean, it's attracted to the to the proton. Why doesn't it just fall in there? Well, quantum mechanics basically, and you can use this uncertainty relation to make a very kind of hand wavy argument, but actually gives you the right value for where the electron prefers to sit, in the ground state at a distance that's about the Bohr radius away from the nucleus. But it's kind of fun. So you just write down the energy, right, and then that if it's out at this orbit again, it's kind of uncertainty in its position. Is about R, or at least that's the scale of it. And so then that gives you an automatic bound on the uncertainty on the momentum, which is about H bar divided by R. If you plug that in, you automatically get a function of R that's no longer just minimized at R equals 0. See, if you ignore this P, right, this Coulomb guy, it wants R to be small, right, because then this becomes big and negative. But that's rescued by the uncertainty in the momentum. You can't put the electron into a smaller and smaller confined space because that makes its kinetic energy bigger and bigger. You can't trade off the potential energy for the, you can't just minimize the potential energy without increasing the kinetic energy as you confine things. So this is another reiteration of what I talked about, back in chapter 1. You can't confine an electron in smaller space. But here, it's explicitly using the uncertainty relation to sort of demonstrate that for the Bohr atom. It's a silly example, but I don't know, it's kind of fun. Okay, any questions about the silly example? We'll do the full-blown calculation for this energy later, but anyway, already this position and momentum stuff can give you some nice tools to at least do back of the envelope type calculations there. Little thought experiments. Common theme that in quantum mechanics, as you try to minimize a potential energy, you end up, because of the uncertainty relation, getting a larger kinetic energy. Unfortunately, you can't. So you can't put an electron in there with the proton to minimize its Coulomb energy without having problems with the kinetic energy. And that's the trade-off between the kinetic part, which is the momentum, and then the potential part, which is the position. So that's kind of the essence of the uncertainty relation. But the wave packet stuff where it gets really interesting is when you think about time evolution. So put this in green now. Whatever happened to time evolution, right? We sort of have mentioned it a little bit when we did the unitary evolution, stationary states and stuff, but we know that the evolution of an arbitrary state is just given by Schrodinger equation, and I derived this for you using kind of first principle, or just like thought. We did it with pure thought. We derived this from pure thought that this must be some Hermitian operator, but I didn't prove to you that this is the energy operator. And that part's a little bit harder to argue. We just showed that it's some Hermitian operator. So we know it's an observable at least. And you can kind of argue this from the correspondence principle. The correspondence principle is just something that says that, quantum mechanics must reduce to our notions of classical mechanics in the appropriate limit. And so if we have some quantity Q, then this expectation value of Q should behave, right? It should correspond to a classical quantity which I'll call QC, and I'll as a function of time. So it could be something like, right, this could be like a position operator. So if we take the expectation value of the position operator, well, that thing, if we have a state that represents a localized particle, then that should just give you the location of the particle. And if we evolve the state in time, however that expectation moves, that should be the same way that the classical position of the particle moves. That should be the correspondence, right? I mean, that's the only way it could make sense. There should be some limit in which quantum mechanics reduces to classical mechanics, and it should be the expectation values of observables, right? Because that's what you can measure. You can't measure the observable itself, right? The observable tells you how you can make measurements. You have to, but it's not. It's not. The object itself is an operator, it's not a number, so that doesn't. So the correspondence is between expectation values of observables, operators, and classical quantities. And so then what we can do here, and this is the kind of thing you did on your homework for that famous theorem, which is the Feynman-Hellman theorem, homework 2. This kind of thing that you sort of looked at, or a similar calculation. We can calculate the time derivative of this expectation value, right? And this is easy. You just do product rule, just like in the homework. The product rule distributes over the derivative over these three things. So you get, minus 1 over IH bar. Psi of t, this hits this psi, brings out an h here, and then the rest follows. We're going to assume that the operator is time independent, so the derivative hitting this thing just gives you 0, and then you get IH bar psi of t q. And now the derivative hits this ket, the last ket, and you just pull out an ht, and so you get basically what amounts to a version of the Heisenberg equation of motion. You can use this kind of stuff to derive. If, for instance, these Browns and Kets lets you do everything. In undergrad quantum, typically people make a big deal about like the Schrodinger picture or the Heisenberg picture. Well, all that stuff is just different ways of interpreting Bras and Kets, right? You can, instead of having a time-dependent state, you could undo the time dependence. Remember that any psi of t is that unitary operation acting on the initial state. So if you bring back these u's and use the Schrodinger equation, you can derive things like, you can make the operators then be the things that's time dependent, because now this u will be a u as a function of time. And so then you can interpret, right, operators, instead of having like this h of t, if you put back in the u's, you'll get basically, u dagger h u as something that you can interpret as a time evolving, an operator that evolves in time. And then this is, the Heisenberg picture version or whatnot. Well, in this case, we'll talk about that later, I guess, but just want you to see a little bit that it's all kind of there. But forget that. Let's just go back to this for now. We'll go back to Heisenberg picture and all that later. But the point is, we're deriving this equation of motion for the expectation value of an operator. And this thing, h bar is just the expectation value of the commutator, right? Q, H, with respect to the psi of t state. So, what about the classical version? The classical version, if this is some coordinate, like a position, the classical version is Hamilton's equations. And if you remember from classical mechanics, this thing, the evolution of the classical version of this, of some coordinate, is given by so-called Poisson brackets with the Hamiltonian, the classical Hamiltonian. And these are called Poisson brackets. Not so important that you know this. And what that looks like is these typically depend on, these generalized coordinates will depend on the phase space variables, position and momentum of your classical system. So what the Poisson brackets end up doing is giving you something like this. I should put, this is a classical Hamiltonian. So I forget who thought of this first. I guess it was Dirac. The idea is that if you can make a connection between the Poisson brackets and the commutation relation, modulo and IH bar, then it would make sense to think about this H operator as an energy, because that's kind of what happens for the classical equation of motion for this classical variable, which should be related to the expectation value of the related observable in quantum mechanics. And so this is a kind of way that people have in the past quantized things, which means going from a classical to a quantum system, is that they took the Poisson brackets and, promoted them to a commutation relation, and that's lets you make a connection between the classical quantities and the quantum mechanical ones. But it doesn't always work, actually. This way of going from classical to quantum doesn't always work. It's often that it just gives you a wrong result. So I think starting with the quantum mechanics is probably better, the way we've been doing it. We just started with quantum mechanics instead of trying to go backwards, from classical mechanics and try to figure out what the corresponding quantum mechanics would be. I don't think it's a good way of doing it. That's why I don't really spend much time on it, or talking about Poisson brackets. But if you wanted to know, one way of arguing that H has something to do with the energy operator, is by connecting it back to classical mechanics and seeing that this equation of motion should correspond to Hamilton's equations, where it's a Poisson bracket with the Hamiltonian, which is which is, you know, the energy. Yeah. But I think I will stop here because I'm out of time. And next time we will, well, we'll just take it for granted that H is the energy operator. And we'll look at free particle evolution, right? We'll look at what happens when H for a free particle, right? For a free particle, H should just be, you know, P squared over 2M. We already know everything about P, takes derivatives of wave functions, so P squared takes 2 derivatives. So, you know, it's H bar squared over 2M. There's a minus sign because of the I, and then this gives you 2 little derivatives. So that's what we'll start with, and we'll see, you know, what does that do to the time evolution if we stick it in here and, you know, look at it in position representation. And then, you know, we'll do the typical 1D mechanics stuff that you do in undergrad, I guess. Yeah, anything else? Yeah, do the quiz. That's all I got for today. I think that's a lot for today.